Let's look at the climate belt. And you can see those belts right here. Look, there's the intertropical convergence zone right there. Here is the high pressure zone of hardly any clouds. Here is the cloudy section with those curling, comma-shaped extratropical cyclones. The extratropical cyclones up here. That's at the polar front. That's at about 60 degrees latitude. It shifts north and south, but it's mainly right around 60 degrees latitude. So you can see that in this picture of the world. This one too. Here in the southern hemisphere, we see again the intertropical convergence zone. We have a zone of clear skies. Oh, in the northern hemisphere up there, we see the Sahara Desert. It's a desert because it's at 30 degrees latitude. And then we continue farther south. We see those comma-shaped clouds that are part of the extratropical cyclones. And there's Antarctica. Notice you can actually see the outline of Antarctica because it's not that cloudy. It's a desert. They get a small amount of snow precipitation, but because it's frozen all the time, it just sticks around and turns into glaciers. Here's another picture, and you can see the same particular pattern. This one has Hurricane Katrina in it. There's the intertropical convergence zone. Here are the extratropical cyclones. Here's the high pressure zone of hardly any clouds, and typically an area where you would have deserts. Here's another high pressure zone in here, and you see that big desert there caused by that high pressure. In January, we see the winds. Each of these arrows is a wind. The size of the arrow is how fast it's moving. This long an arrow would be 10 meters per second of speed, and so shorter arrows are in proportion to that. Longer arrows would be faster winds. And you see that pattern of winds we've been talking about. Here's the northeast trade winds, the southeast trade winds, the westerly winds, some more westerly winds in the northern hemisphere. And if we look at this one, this is in July, still have the same pattern, but things have shifted a little bit farther. The main difference between these two, if we go back, look here. There's a really big difference right there. This is the monsoon. Okay, monsoon is a wind. During the winter, the wind is coming off the land and it's a dry wind. During the summer, the wind is coming off the ocean and it's a wet wind. And that's why people think the word monsoon means rain, but it actually is a wind. This is the Köppen climate classification system. And you don't have to memorize this, but you can see that people have classified many, many details, and each of these letters represents a different type of climate conditions. So that kind of maps out the different climate areas. You can see in this belt, that's pretty darn wet, and they've represented that by blue colors to represent the water. And then in this belt, we've got red colors representing deserts, so these are desert type environments. And you have that both in the northern and southern hemispheres. And then we have the temperate zone here, which is mostly ocean. And then we get into what's called the boreal forest. This is the area where you have lots of rain and snow, mostly snow, from the 60 degrees latitude, and that's created a forest. Forests like lots of rain. Okay, where else is there forest? There's forest there, and there's forest here, right? The tropical rainfall forest. There are also rainforests along coastal areas. Some coastal areas have rainforests too, but that's special conditions, special situation. We don't have forests in the southern hemisphere of the boreal type. Well, first of all, boreal means northern, but also that style of forest doesn't occur because it's ocean down there. And then we have the tundra zone here. These are tundra climates. And here it's actually mostly ice, as the ice has overrun the area where the tundra would be. And then you get to the polar regions where it is just all ice. Or open water up here. Sometimes during the summer there's some places where the water opens up. Now biomes are large-scale ecosystems, such as tropical rainforests or boreal forests. And this shows you the different forests and grasslands and deserts. Let's talk about jet streams next. A jet stream is a band of very fast-moving air. It's maybe 160 to 320 kilometers per hour, or that would be 100 to 200 miles per hour. It's at the top of the troposphere between the cells. This is a place where there's a high temperature gradient, meaning there's a big difference in temperature from one location to the next nearby. These winds are westerly winds. That means they're flowing from west to east. They can also shift to the north or to the south, but mainly from west to east. The band is several hundred kilometers wide, and jets use them when traveling east. So there's a jet traveling east. Obviously, you would gain some speed if you traveled in the jet stream. Coming back the other direction, you want to avoid traveling the jet stream because it would just slow you down. So the actual physical length of time it takes to travel across the country is a lot longer going from east to west than it is going from west to east.
Poleward of the subtropical highs lay the mid-latitude regions in both hemispheres. The mid-latitudes are characterized by a relatively strong flow from west to east above the surface of the Earth, called the jet stream. Within the jet stream, disturbances form that we call mid-latitude cyclones. These are regions of low pressure, and they have circulations that, as a result, tend to evolve these comma-shaped cloud patterns, seen here and here. Winds around these mid-latitude cyclones blow around the low counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. These cyclones tend to move along with the jet stream from west to east, with the comma shape becoming more pronounced and wrapped up as the cyclone evolves. The jet stream forms along the strong gradient in temperature between cold polar air and warm tropical air in each hemisphere. Thus, the jet stream also is a manifestation of the strong gradient in temperature. So, poleward of the jet stream, the air tends to be cold, and equatorward of the jet stream, the air tends to be relatively warm.
Now there are 4 jet streams, 2 for each hemisphere: the polar jet, the polar jets, and the subtropical jets. The polar jets are stronger. The average locations are roughly between the Ferrel cells and the polar cells. That's for the polar front jets, also shortened to polar jet. And there's 2 of those, one in each hemisphere. That's right there between the polar cell and the Ferrel cell. Now, one thing we haven't talked about is how thick the atmosphere is, or the troposphere is, and you'll notice that in this diagram you can see that at the equator the troposphere is quite a bit thicker, and towards the poles the troposphere is quite a bit thinner. And that has to do with the spin of the Earth. That's just a little aside. So we have the jet stream traveling right here at the top of the Ferrel cell next to the polar cell. That's where there's a big temperature gradient, a big change in temperature, because think about it, this air is coming from the subtropical regions, and this air is coming from the polar regions. So those 2 air masses are very different in temperature. That creates a large temperature gradient. That's what causes winds, temperature gradients. This little bullseye look is supposed to illustrate the idea that the wind is traveling into the screen here. Okay, so the 2 subtropical jets between the Ferrel cell and the Hadley cell. And these jets are all close to the tropopause, just under the tropopause, or right there near the tropopause. The jet streams are stronger in winter and weaker in summer. Polar front jets occur above cold fronts and warm fronts. Think about this. If you have a wobble in the jet stream, then where the wave of air is moving, so that warm air is replacing cold air, then you're going to get a warm front. And if that wave moves in such a way that cold air replaces warm air, then you get a cold front. Jet streams are caused by strong pressure differences in the upper troposphere between the cells, and that's caused by that temperature gradient. Jet streams move north in the northern hemisphere spring and summer, and south in the northern hemisphere winter. They kind of follow the sun a little bit. Now the wiggles, or wobbles, or waves in the jet stream are called Rossby waves. This diagram shows the jet stream right there, where there's lots of arrows close together. This wobble here is a Rossby wave. Rossby waves are giant meanders in the high altitude winds. This map shows winds at where the pressure is 500 millibars. That's just about half of the atmosphere is above and about half of the atmosphere is below. And remember that sea surface air pressure is just about 1,013 millibars, and so this is about halfway up in terms of molecules in the atmosphere. The jet stream is the fastest core of the wavy flow of the Rossby waves. Okay, so this fastest core here, that's the jet stream. The period of the Rossby waves is the amount of time it takes between successive weather events. Okay, a period, like a time period. So how much time does it take between one wave and the next? How much time is it between this wave and this wave? So this wave arrives, and then this one's traveling, it's moving, and it gets here. How long did that take? Some climate change questions arise with decrease in difference in temperature between the poles and the equator. So as climate change is happening, the poles are warming faster than the equator. That means the difference in temperature between the poles and the equator has decreased. When that decreases, that's going to decrease the surface winds. And with decreased surface winds, or even upper level winds, then that's going to slow down the Rossby waves. And here's the question. Has planetary wave activity changed in recent decades, or is it likely to do so under projected future warming? And if it is changing, is the rapid Arctic warming indeed responsible for that change? So in other words, if you're warming the Arctic, you're decreasing the difference between the Arctic and the equator. Is that causing a slowing of the Rossby waves? There's a Wikipedia article about this topic. This is an article by Michael Mann about Rossby waves. This was published in March 2019 in the Scientific American. And I have that article posted on Moodle for you. It looks like Rossby waves are increasing in amplitude. So the wiggle is bigger, and they're also slowing down. So they're not progressing from one place to another as fast. That means that we're going to get extreme events. And this is a quote from Michael Mann within this article. During the extreme events I noted, the jet stream acted strangely. The bends went exceptionally far north and south, and they stalled. They did not progress eastward like they normally would. The weather amplifier, Rossby waves. You should read this article. It's very interesting.